Hello, class. Welcome back to the semester. And let's dive into the last lesson of the second stage. Remember that we are still on the second stage, which is kinematics and the laws of motion of the bodies. We have seen many things, okay? Just a brief overview. We have seen some concepts such as system of reference, the particle model, translational motion, scalar and vector quantities, what is distance, what is displacement, what is the difference between them. Can you remember this? If a particle goes from here to here, all of this is the distance traveled, and the length of this straight line is the displacement. I hope you remember that, or I hope that you remember it now that I'm telling you. We have seen the difference between speed and velocity, acceleration, and then we took a look right before going to vacations. We took a look at inertia and mass, the concept of force, which I'm going to remind you right now quickly. Force is any influence applied on a particle that will make it accelerate. For example, if this is your particle, the soccer ball, then when you kick it, basically what you're doing is applying a force on the soccer ball, and therefore it's going to accelerate. You're going to change the velocity of this ball. Okay, that's basically the whole idea about force. And now we're gonna take a look at the three laws of motion of the bodies, also known as the three laws of Newton or the three Newton laws, which you may have heard already in junior high. So this is basically just a reminder of these three laws. So let's get down to it. What is the first law? The first law says the following. A body, let me go my pencil. It says a body or a particle will remain at rest or moving with uniform rectilinear motion unless acted upon by a force. So basically what this law is saying, guys, is that we can have two cases or two scenarios. I'm gonna draw a body, just a simple box. That's it, just a little box. In this case, let's suppose that this box is at rest. What that means is that in this frame of reference, in the frame of reference of, let's say, this table, this object is not moving. It's at rest completely. What this law is telling you is something very intuitive, which is this, that the box will remain at rest unless a force comes and acts upon this body, which we know, right? I mean, that's how objects behave. They're going to be laying there at rest unless something disturbs that that state of motion, right? So that is the first case in which the object is at rest. But there's another case, guys, which is perfectly valid also. The second case is this, that the object is already moving with uniform rectilinear motion, and if you remember what that is basically going in a on a straight line, moving in a straight line with uniform velocity. What that means is that basically it's gonna travel with constant velocity. Let's suppose this object is moving over this floor at constant velocity. Therefore, we say that it's having URM, and it's gonna continue doing so unless acted upon by a force. It's gonna continue doing that. Now you may ask me, that's not how I observe things moving, right? For example, if you have something on your desk and if you push it, then you're gonna observe that it comes to a stop very quickly. Why is that? Well, the reason for that is that there is friction between the floor and the object. You see? But if there was no friction, if there was no force, then this object will continue moving in the same way for all eternity, unless something acts on it. In other words, unless something applies a force on this object and changes such state of motion. So basically we have these two cases. An object will remain basically in its own state of motion unless something comes along and applies a force on this object. That's how it works. This is known as the law of inertia, because basically what it's telling you is that the object will continue moving as it was moving unless a force comes and is applied to the object. Okay, the second law, this is perhaps the most interesting one. The second law says the following: the force being applied to a particle is equal to its mass, the mass of the particle, I mean, times its acceleration, the acceleration of the particle. The unit for force is the Newton. So suppose this, guys, you have a particle, again, you have a little box, and you observe that this particle has an acceleration. It's moving with an acceleration a, and you also know that the mass of this object is m. Okay, so this second law tells us that we can actually measure the force being applied to this object, and there should be a force, right? Because remember that a force is something that causes acceleration. If this object has an acceleration a, that's because there is a force being applied to it. Okay, there is a force F being applied on this object so that this object has an acceleration. Okay, whenever you see that something has an acceleration, that means that there is a force being applied on such object. Now, how do I find this force F, the magnitude of that force? Well, this second law provides me the, the rule or the law. It says the force being applied to a particle is equal to its mass. It's equal to its mass, the mass of the particle, times its acceleration. And since I already told you that the acceleration of this particle is a, then it would be like that. Force equals mass times acceleration. This is the second law of motion, guys. Basically, all of these words, are basically comprised or set in this basic equation. Force equals mass times acceleration. And the unit for force is the Newton, represented by an N. What is a Newton? 1 Newton is equal to 1 kilogram times 1 meter per second squared. Okay, like this. Okay, this is a unit of force, like this. This is a unit for mass, which is in here, and this is the unit for acceleration, which is right here. So 1 Newton is equal to 1 kilogram times 1 meter per second squared. And this is the second law of motion. We're going to use it in a moment in order to calculate forces and accelerations and etc. And finally, the third law of motion, which is a law that is often told as for every action there is an equal and opposite reaction. What does it say though? It says this: for every force there corresponds another force equal in magnitude but opposite in direction. What is that? Well, basically, guys, what this law is telling you is that forces always appears in pairs. Look, it's like we have it here. Forces always come in pairs. When this foot applies a force on this ball, let's suppose that the force is along this direction, okay? So what I'm doing here is representing with this arrow the force that the foot applies on the ball. This is of that force. It's a visual representation of that idea. Okay, when that happens, guys, we also have, let's say, the opposite, which is the ball hitting the foot in the opposite direction and with the same strength. That's why I'm drawing the arrows with the same length, more or less, okay? These two arrows are in opposite directions and they are of the same length, signifying that these two are forces which are equal in magnitude. They are of the same length, but opposite in direction. Okay, again, this is the force representing the force applied on the ball by the foot, and this arrow is the force that represents the force that the ball applies on the foot, and they always come in pairs. This is always the case. That's why you feel something when you hit a wall, or when you hit a ball, or when you hit anything. That's why you feel something, right? It's because that other object is also hitting you. It's also applying a force on you. Let's look at this image. We have a swimmer and we have this wall. So the swimmer is basically pushing herself by applying a force on the wall. Okay, so basically with her foot she's applying a force on the wall in this direction. Okay, and by doing so, and due to the third law of motion, we have that the wall also applies a force on her in this other direction, and that's why she's actually she can actually move, let's say, faster by doing this motion. By her applying a force on the wall is going to apply a force on her, and therefore she's going to move, or she's going to accelerate towards the left. In this case, we have this stick figure applying a force on the wall, and the same idea. The wall will apply a force on him of the same magnitude, but in opposite direction. Okay, that's basically the idea. So for example, if force 1, which is the force applying by the stick figure to the wall, is of 5 newtons, let's suppose that, okay, this force is 5 newtons, then this other force, which is the force applied by the wall on the stick figure, will also be of 5 newtons, only applied in the opposite direction. Okay, so for every force there corresponds another force equal in magnitude but opposite in direction. And this is what you can observe when you have a gun recoil. uh, I suppose, I don't know if you have handled a gun. I suppose not, because it's not very common in Mexico, but you have perhaps observed this phenomenon. When you handle a gun, guys, and when you shoot it, this may happen. Why does that happen? Look at that. This is known as a gun recoil. Look at this one. This is very common on unexperienced people shooting guns or rifles or whatever. It's very common. What is happening here? In the previous case and in this case and in all of the other cases, what is happening is this, guys. You have this gun, right? So I'm just gonna uh, uh, draw this surface, okay, in order to represent the gun. And inside there is a bullet. Okay, so we have gun and bullet. Try to only put that in your mind. Like, ignore everything else. We just have the gun and the bullet inside the gun. What is happening when she triggers, when she fingers the trigger, when she actions the gun? What is happening is that the gun is applying a force on the bullet, and that's why the bullet accelerates to the right. Okay, the gun applies a force on the bullet. And due to the third law of motion, we must also have the contrary, or the opposite, right? The bullet applying a force on the gun. In what direction? In this direction, in the opposite direction. Let me actually draw the bullet in blue. This is the bullet in blue, and this is the force applied by the bullet on the gun. If the gun applies a force on the bullet in this direction, then therefore, by the third law of motion, the bullet will apply a force on the gun in the opposite direction. And that's why you observe the gun pushing backwards, okay, or going backwards. And if the person is not experienced well enough, she's gonna harm herself, right? Let's look at that again. You see, that's exactly what's happening. It's basically the third law of motion at work. You see? So what you need to do in these cases when you handle a gun is basically have a even soldiers. Wow, that's extremely dangerous. That's why you have to be in the hands of experts when you handle a gun. If you don't know how to handle a gun, it can be very dangerous. And it's just physics, right? It's just physics. It's basic physics. So don't ignore the laws of motion, guys, because it can be dangerous. Okay, now let's look at three examples, guys. Three very quick examples of these laws so that we can finish this stage. So exercise number 9. It says, find the force F applied to a body of 10 kilograms. Let's draw the body. We usually just draw boxes when we do this type of exercises. So this is a box of 10 kilograms. So we have the mass, and we know that this box is having an acceleration of 2 meters per second squared. So the acceleration of this body is 2 meters per second squared. This is the mass, we have it. This is the acceleration, we have it. And they want me to find the force being applied on this object. So what I do is I use the second law of motion, which once again is force equals mass times acceleration, and thus I can find the force. Force is just going to be the mass, which is 10 kilograms, times acceleration, which is 2 meters per second squared, and therefore the force will be the multiplication of these two quantities. That's going to be 20 kilograms per, times meters per second squared. And remember that the units, or well, this unit, kilogram times meters per second squared, is called 1 newton, and so this is 20 newtons. So that is the force being applied on this object, and this force will produce this acceleration on this object. Okay, next exercise. Exercise number 10. It's a very similar exercise. Find the acceleration of a particle of 20 kilograms. Let's draw the particle. Let's write down its mass, 20 kilograms, if there is a force of 5 newtons applied to it. So now we have the mass of the particle and we have the force being applied on the particle, which is 5 newtons. And they want me to find the acceleration of the particle. If we have a particle of this mass and we apply a force of this magnitude to such mass, what will be the acceleration? Once again, I use Newton's second law, F equals ma, and I substitute whatever quantities I have. I have the force, which is 5 newtons, being equal to the mass, which is 20 kilograms, and times the acceleration. So that's it. Can you see? Basically, all we have to do is isolate the acceleration. Acceleration equals 5 newtons over 20 kilograms. And therefore, the acceleration will be 5 over 20, which is 0.25. 0.25 or 1/4 meters per second squared. That's it. That's how you use the second law of motion in order to solve very simple problems. And finally, exercise 11 is about this. Find the weight of a body of 2 kilograms that is close to Earth's surface. So this seems like an unsolvable problem, right? It seems like we don't have enough information to solve the problem. Okay, let's see. Let's remember first of all, what is the weight of a body? If you remember, guys, I had already told you that the weight of a body is this. When anybody is on the surface of a planet or close to the surface, like it doesn't have to be strictly on the surface. It doesn't have to be here. It can be, I don't know, some kilometers away. That's what we know as close to the surface. Um, then the planet or the star or whatever this object is, this celestial object, will apply a force on this object. Will apply a force towards its center. Okay, if the object was here, then the force would be applied in this direction and so on. And this force is known as the weight of this body. Okay, so weight is a force that the planet Earth applies on this body if the body is close to the surface. Okay, it can be at the surface or on an airplane or at the top of Mount Everest, something like that. And the more you get further away, the less weight you will feel. So how do I find the weight of this body? Well, since weight is a force, then it has to follow the second law of motion. Okay, this is the second law of motion. Force equals mass times acceleration. If the weight is a force, then the weight has to follow this same rule. In other words, the weight has to be equal to the mass of the object times the acceleration of the object. But we know, or I mean, perhaps you know, that the acceleration that a body experiences close to the surface of the Earth is about 9.8 meters per second squared. 9.8 meters per second squared, which is known as the acceleration due to gravity, right? So therefore, all I need to do, guys, is substitute this acceleration by this number, because this is the acceleration that a body will have close to the surface of the Earth. So let's make that substitution. The weight of this body is going to be its mass times this acceleration, which is g, the acceleration due to gravity. And that's it. We have a formula to calculate the weight of any body. The weight of any body close to the surface of the Earth is going to be its mass times the acceleration g, which is acceleration due to gravity, which is 9.8, very close to the surface of the Earth. So that's it. We substitute what we know. The mass is 2 kilograms, and g is 9.8 meters per second squared. And therefore, the weight is going to be 2 times 9.8, which is 19.6. Weight, being a force, has to have units of newtons, and I'm done. The weight of this body, of this particular body of 2 kilograms, is going to be 19.6 newtons close to the surface of the Earth. If this body were put very further away from the surface, like a lot of kilometers away, this would change. This would be less. Okay, just take that into consideration. Okay, guys. So that's basically how the second law of motion works, and that's how the three laws of motion work. So let me go back with you for questions, and this would actually be the last lesson in this second stage, guys. So thanks a lot.